Today we're headed into the second method of factoring. So again, just a reminder that factoring is the opposite of polynomial multiplication. So today we're going to see things more like FOIL, but a very specific kind of FOIL. So, or at least problems that have something very particular happen. So here's an example of one of those. So remember that for FOIL, that's where we did first, outside, inside, last. So x times x makes x squared. X times negative 6 will make negative 6x. 6 times x is 6x. And 6 and negative 6 would make negative 36. Now, the special thing about today, or at least this kind of FOIL, is that the center section right here, negative 6x plus 6x, actually cancels out when we combine it. So we just get an answer that ends up having two terms, x squared minus 36. Things to notice about this is that we have the same number here, which is cool. Just one is positive and one is negative, which is what causes this to cancel out, and also is what causes this to be a perfect square for this number. So 6 times 6 makes 36, and that is a perfect square. So perfect squares are going to come into play big time today. We're looking at part number 2, which is difference of perfect squares. Now, this method is kind of specific. It doesn't get used as often because your problems have to fit a certain format. But it is a fan favorite. It tends to be the easiest method of factoring for most people. Now, in order to use this method, these are the criteria that you have to have. It's called difference of perfect squares for a reason. So the first thing you need is subtraction, going right along with difference. The other thing that you need is perfect squares. As you move through your math journey in high school and probably beyond as well, this part gets a little looser. You won't necessarily have to have a perfect square to make this method work. It does get a little trickier after that, but that's beyond Algebra 1. So we're going to do that with just perfect squares here today. So just to recap square roots for a second, that's going to be really important. That's how we're going to end up factoring. So if I take the square root of 49, that's 7. And that's because 7 times 7 makes 49. The square root of 4 is 2. Square root of 1 tends to throw people off for some reason. It's just 1. It actually doesn't change. 1 times 1 is 1. And you'll see some bigger numbers sometimes too, like 144, and the square root of that is 12. The newer part might be for variables. The square root of x squared is actually x. That's the one that comes up the most often. And that's think about what made that. X times x is what makes x squared. So that would make the square root of x squared, just x. For x to the 8th, its square root is actually x to the 4th. And you might notice a pattern here. And that's because x to the 4th and x to the 4th, if you multiply those, make 8 because you add these together. So if you're trying to find the shorthand way, just divide by 2. So if I take 20 divided by 2, I get 10, because 10 plus 10 makes 20. And even if you're looking at really big numbers, you would still just divide by 2. All right, so in this section, remember, we can have things that are prime, but we've added some criteria from our last video. So in the last video, we just needed a GCF of 1. Okay, and that's still true. If you only have a GCF of 1, it could be prime. But the other thing that's a giveaway to prime problems in this one is that those also have to be added. So if you see addition instead of subtraction, it's got to be prime. All right, so do make sure that you always check for that GCF first, so that will still connect to each of our other methods. So here are your general steps. First, we're going to check for that GCF. A lot of times it's not going to have one, or its only GCF will be 1. If it does have one, go ahead and follow the process for finding a GCF. If it doesn't have one, go ahead and move to the second step. That's just to make sure that it meets the criteria. Are you allowed to use this method? So make sure that you look for those perfect squares and make sure that you see subtraction in between. All we have to do to find our answers from there is take square roots, and your answer is going to actually be 2 binomials, so it will look kind of like a FOIL problem when we're finished. The other key thing to know about this method is as you're making your 2 binomials, one will be a positive and one will be a negative. So you'll end up with a plus sign in one and a minus sign in the other. And we'll talk about why that's important here in a few minutes. So if we look at x squared minus 36, all right, first, if I look for a GCF, I have 1 and 36, so its GCF is 1. And if I look at my variables, we have x squared and no x happening there, so there's only a GCF of 1. However, it's not prime. I can move down the list now, and I'm going to check the format. So I'm looking for a perfect square. Okay, x squared is a perfect square. 36 is also a perfect square. And we need to check for subtraction, all of which I have here. So all we need to do is take square roots to make our answer. So I go ahead and I draw my two binomials first, just to kind of get ready. As you practice more, you'll make them the right size. They won't be too big or too small. They'll be close to just right. So I'm going to go ahead and square root what I need to square root. So the square root of x squared is x. Since x squared was in the front, I'm going to go ahead and put that x in the front as well. Then I'm going to square root 36, and that gives me 6. I'm going to put a 6 in the back of each of my binomials. And then this is where this little step right here comes in. We're going to make one of them positive and one of them negative. What the positive and negative do is this back up here. So we actually factored the problem that we multiplied back at the top of our page. So having one positive and one negative is what causes this to cancel out in the middle and gives us the problem that we're looking for. If you keep two positive 6s or two negative 6s, first you end up with a positive 36, which is not what we have, and your middle term doesn't cancel out. So that's why we have to have one of each. The order isn't so important. You could put the subtraction one first, so this could say x minus 6, x plus 6, and that's totally fine as well. I'll go ahead and flip it for the next one. So again, I don't have a GCF other than 1, and I do have perfect squares being subtracted. So I'm going to go ahead and put my y's in the front after square rooting that. The square root of 4 is 2, and we make 1 minus and 1 plus. Now on the next one, I'm looking for a GCF, still don't have one other than 1, and that's fine. But it's when I check the format. I do have perfect squares, but here they are not being subtracted, they're actually being added. So this one counts as prime. I don't have the space to show you all of the different combinations that people try to tell me. Most people go for the plus and minus 5 because they aren't really paying attention. It is a very subtle change. But what happens is the middle term cancels out and you end up with minus 25. So you don't get a match if you were to multiply your answer back through. Then people are like, say, okay, well, since it's positive, maybe I need plus 5 and plus 5. Well, we kind of just discussed if I have plus 5 and plus 5, they don't cancel each other out. So you'd end up with a middle term. The same thing happens if you make them both negative. You end up with just a negative term in the middle instead. So that's why this has to be prime. No combination can give you both a positive number here and have a positive and negative that will cancel out in the middle. All right, even if we throw a number on the front, as long as that number is a perfect square, we're still good to go. 9 and 64 don't have anything in common. This just has 1, 3, and 9. This has far more than that, but none of the numbers are 3 or 9, just 1. Also, no x's there, so this one will just look a little bit different. Okay, I'm still going to take square roots. The square root of 9 is 3. Since the 9 was all the way in the front, the 3 is also going to go all the way in the front. Attached to that is going to be the x. Because the 9 was attached to the x squared, the 3 and the x are also going to be attached. The square root of 64 is 8. We're still going to make 1 plus and 1 minus. Same thing happens on the next one. Still no GCF. We do have two perfect squares being subtracted, so we're going to go ahead and take square roots. So the square root of 4 is 2. The square root of g squared is g. The square root of 81 is 9. And we're going to make 1 plus and 1 minus. All right, the last way they can make this even more complicated is by throwing double variables in there. And it's really not much different. 16 and 121 don't have anything in common. X and Y don't have anything in common either. So I can go ahead and take my square root. So the square root of 16 is 4. Square root of x squared is x. Okay, those are connected just like in those last couple of problems. Then the square root of 121 is 11, and notice how I leave a little bit of space in the back. That's just so that I can square root y and attach that to. We still keep 1 plus and 1 minus. All right, the same thing happens on the next one. Square root of 49 is 7, like we mentioned up in our square root practice. Attached to that will be the x. Square root of 9 is 3. Attached to that will be a y. And we got 1 plus 1 minus. All right, this is where it changes a little bit. What you'll see now is you still see subtraction, but this time we do have a GCF. Usually the GCF problems, in these anyways, give themselves away because you get numbers that aren't perfect squares. Or you'll see some wonky exponents that aren't just 2 or they're not even numbers. So that can kind of lead you in the direction to say, wait a minute, there's probably going to be a GCF here. So if I look at 48 and 3, both of those have a 3 in common. So I'm going to treat this like a GCF and go ahead and divide out that 3. So 48 divided by 3 is 16, and 3 divided by 3 is just 1. So now if I look inside of my parentheses, I do have perfect squares that are now being subtracted. So this problem actually has 2 steps. The first step was to take out that GCF, and now I'm going to factor the rest of this like normal. So the 3 is a factor of my problem. It has to stay as part of my final answer. But then I can break down the rest of this like we've been doing with difference of squares. So the square root of 16 is 4. Attached to that will be our x. The square root of 1 is 1, and we make 1 plus and 1 minus. If you leave off the 3 and try to multiply it back through, you only get to here, which doesn't match your original problem. That's why your 3 has to stay part of your final answer as well. In the next chunk, we do have both pieces acting as part of our GCF. We have a number and a variable. So 2 and 8 both have a 2 in common. And between x to the 7th and x to the 5th, 5 is the smaller exponent. So I'm going to go ahead and divide those out. It will adjust my exponents to now be perfect squares, which is pretty cool. So I'll have x squared minus 4 in the middle. The 2x to the 5th does have to stay part of my problem. But then I should be able to factor and say x plus 2 and x minus 2. Now, don't be misled. If you see a problem like this, it doesn't initially scream GCF to me because I see 100 and I see 16, both of which are perfect squares. So I'm very tempted to go ahead and factor right away. However, these terms do have a GCF, which is why it's important to check for it anyway. 116 actually have a 4 in common that I can take out. And after dividing, I'm still left with perfect squares on the inside there. Now the catch with this one, and what they'll do generally in testing situations, is in the instructions, they'll say something along the lines of factor completely. If you just factor this and make it 10a plus 4, 10a minus 4, it will likely be an option, unfortunately. However, it won't be factored completely. Both of your chunks would still have something in common that you could take out. So this is your most completely factored form. Okay, making sure that you check for that GCF. If you're feeling good about this, now's a great time to pause the video and try the next two, just to kind of point you in the right direction. This first example kind of works like these two right here. And your second example is going to be very similar to this one right here. All right, if you've taken a moment to give those a shot. All right, your first answer should be something like 5x plus 4 and 5x minus 4. Okay, again, if you have 5x minus 4 and 5x plus 4, you're doing great. On the next one has 2 steps. This one has a GCF of 2m cubed. And then on the inside, you'll have 9m squared minus 1. But then remember, we need to keep going to break this down completely. So the 2m cubed should stay part of your problem. And then you'll break down the second part into 3m plus 1 and 3m minus 1.